Welcome to this masterclass on mathematics for economists. Today, we delve into one of the most powerful tools in an economist's arsenal, the partial derivative. In the real world, the economy is a chaotic web of interconnected variables. To make sense of it, we use the principle of Ceteris Paribus, a Latin phrase meaning all other things being equal. Partial derivatives are the mathematical embodiment of this principle, allowing us to isolate the effect of one variable while holding everything else constant. In economics, we rarely deal with functions of a single variable. Consider the gross domestic product, GDP, of a nation. It isn't just a function of investment, it depends on consumption, government spending, and net exports. Mathematically, we express this as y equals f of c, I, g, and x. To understand how a change in interest rates affects investment, without being distracted by changes in government policy, we need a way to freeze the other variables. This is where the magic of partial differentiation begins. Let's define the partial derivative formally. Suppose we have a function z equals f of xy. The partial derivative of f with respect to x is defined as the limit as h approaches 0 of f of x plus h comma y minus f of x comma y divided by h. Notice the key detail. The variable y remains unchanged. We denote this as derivative f divided by derivative x, or simply f sub x. It measures the instantaneous rate of change of the dependent variable with respect to one specific independent variable. To visualize this, imagine a three-dimensional surface representing a production function. The vertical height represents output, while the two horizontal axes represent labor and capital. If we want to find the marginal product of labor, we take a slice of this mountain parallel to the labor axis. This slice creates a two-dimensional curve. The slope of the tangent line to this curve at any point is our partial derivative. It shows exactly how much output increases for a tiny addition of labor, assuming capital is fixed in place. Let's look at a practical example, the law of demand. Usually we say QD equals F of P, but in reality demand also depends on income, I. So QD equals F of P comma I. If the price of a luxury car increases, demand usually falls. But what if, at the same time, everyone's income doubles? The total demand might actually rise. By using partial derivatives, an economist can calculate derivative QD divided by derivative P, which isolates the price effect, confirming that, ceteris paribus, price increases lead to lower demand. One of the most famous functions in economics is the Cobb-Douglas production function, y equals a times L to the alpha times k to the beta. Here, y is total production, L is labor, and k is capital. The partial derivative, derivative y divided by derivative L, gives us the marginal product of labor, MPL. According to empirical studies for the US economy, alpha is often estimated around 0.7, meaning that labor accounts for roughly 70% of total income. Partial derivatives allow us to prove the law of diminishing marginal returns. As you add more labor to a fixed amount of capital, the partial derivative FL eventually decreases. Moving beyond first-order changes, we have second-order partial derivatives. These tell us about the curvature of our economic models. For instance, derivative squared f divided by derivative x squared tells us if the marginal utility is increasing or decreasing. Even more interesting are cross-partial derivatives, like derivative squared f divided by derivative x divided by derivative y. In economics, these reveal if two goods are complements or substitutes. If the marginal utility of coffee increases when you have more sugar, the cross-partial derivative is positive, signifying they are complements. In conclusion, partial derivatives are the bridge between abstract mathematical theory and real-world economic policy. They allow us to construct models of optimization, solve the Lagrange multiplier problems for consumer choice, and understand the complex dynamics of global markets. Whether you are analyzing a firm's cost structure or a nation's growth path, you are looking at Ceteris Paribus in action. References: Alpha C. Chang and Kevin Wainwright, Fundamental Methods of Mathematical Economics. Hal Varian, Intermediate Microeconomics, A Modern Approach. Andrew Mas-Colell, Microeconomic Theory. Gujarati, Basic Economics.